Hi, everybody. Just give it 1 minute and see if anyone else comes in. If not, start it. Okay, let's get started and see if anyone else comes in. Hi, everybody. Welcome to week 3. This week is probably the last of the easy short seminars, maybe half an hour to 40 minutes. Whereas next week, which we look at bonding and molecular geometry, that one will probably, I'll be doing that in 2 parts as a pre-recording, 40 minutes each. So, this is the last of the easy ones. You want to get into the nitty gritty after this. So, a current and what our atomic theory has always been based on is all matter is composed of small, fast-moving particles called atoms. And we've had, I don't know, I'd hate to think how many we've had proposals, but there's been a few main ones, which I'll talk about. I'm big on science history and what's come before us, because that allows us to see where we've come in a relatively short period of time, if you consider what we had to work with even 100 years ago. So, atom comes from the Greek word atomos, meaning indivisible. I mean, we have known about atoms for a very long time, since the 5th century BC, but our understanding of what they were has grown significantly. So Dalton was the 1700s. Tiny indivisible particles called atoms. The atoms of each element are exactly alike and have the same mass. He was kind of right there. But we now know we have isotopes. So he was kind of right. So an atom of one element cannot be changed into an atom of a different element. What's the term? Alchemy. Alchemy was they tried to turn other things into gold, other elements into gold. And we couldn't really until we had particle accelerators, which we can do that a little bit now. But the idea of alchemy, where you can turn anything into gold, is only happens in stars, and even then. So, atoms of different elements can join to form compounds. We know he was correct there. So Thomson's 1890, discovered that atoms were not simple solid spheres. So he thought, change the share. Actually, so Dalton thought, you've got the slides, you can follow. Dalton thought that it was just a sphere. Everything is dead. Thank you to my 2-year-old. So he just thought that atoms were spheres. Thomson came up with the idea that there was within an atom. I think he still thought it was a sphere. I mean, he can't have thought that what we think now, so the cloud of electrons. Hang on, someone's trying to log in. Sorry. Hi, Izzy. Sorry, I was in the zone and talking and didn't see you coming in. So we have Dalton's model. I mean, it was pretty good effort. So tiny individual particles called atoms. He didn't really know what was in here, though. He didn't know what they were made of. He just knew that they existed. So 140 years later, we have Thomson's model. So they contain subatomic particles. So this kind of builds on last week's. But we will go further into the periodic table. So subatomic particles, he said there is a negatively charged particle. Now we're getting closer. So we now have electrons and we have an atom. So we're on our way. So very small negatively charged particles called electrons, smaller than the nucleus. I mean, smaller than the atom itself. So we know that in its normal state, elements are neutrally charged. He was a smart guy. So he went, well, this sphere in the middle of the atom must be positively charged, and the electrons attached there, because then it makes a neutral charge. So close. He thought they were like chocolate chips in the cookie dough, but he couldn't explain that if there was more than one electron, that there would be a negative charge. So we're getting closer. So Rutherford said, hang on, that there's electrons, so we know there's an electronic charge, so there must be a positive charge somewhere. So he said there's a proton. So the protons, he conducted a number of experiments. I mean, we could be here speaking for days just on the experiments to discover this. But the protons were in the middle. Okay, there's a positive charge in the middle. He still didn't really know where the electrons were, but he knew the positive charge came from subatomic particles inside the nucleus. So we're getting closer and closer. So his model was that atom is mostly empty space, which it is. There's very little of, if you take the radius of an atom, most of it is empty. And the nucleus contains all the mass, like a peach. So Bohr's model, B-O-H-R. Electrons are like Shrek, they're layered, they have layers. Or an onion. So we have the nucleus in the middle. And at this point, we still don't know about the neutrons. We still only know about protons. Just make sure you guys can actually see what I'm writing. We have protons. This is where we're going to get serious. So we have the nucleus. And we've got protons. They still don't know about neutrons yet. So he went, this very smart man, Niels Bohr, I think Niels Bohr, that there was energy levels around the nucleus. One, two, three, four, five, six. How do I know there's only 7 of these? Because in the periodic table, there's 7 periods running across. So each electron, or each electron level, has a certain amount of energy that assists it in moving around the nucleus. So we're getting closer to where we are now. And hopefully understanding how this evolved helps understand the periodic table. So the electrons first orbital, the ones here. So depending on how many of these levels it has, depends on how many electrons it has. The electrons can be found by the atomic number. So this one here is the most important. The outer shell, or what we call the valence shell. This is the one that's involved in bonding. For all intents and purposes for your course, you're not really interested in anything else aside from these valence electrons. So this gave us what we call the electron cloud model. So these electrons are flying around randomly around here. Now in the slides I said it gives the nucleus its size and shape. That's supposed to say it gives the atoms its size and shape. Now, how do we know that this is true? Experimentally, of course, but I think the next slide. So X-ray crystallography, I couldn't find any pictures of the research that I did, so I'll just explain it. But we have an atom, or we might have a protein. I'm gonna get rid of this. We can take X-rays. These are X-rays. And we can have, this is a ridiculous representation, but I will hopefully explain. So we have a nucleus here, X-rays. So we have our layered ones in there. We've got electrons here, 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 here. Most of the X-rays will pass through. Those that hit the electrons will bounce off. Bounce off. Bounce off. This one bounces backwards. And here we have a plate, and any of the X-rays that go through hit that plate, back plate. And we can determine the shape of an atom and where the electrons might have been based on where there was no imprint from an X-ray on this back plate. We can also determine the shape of proteins using this method. So we stick a protein, again, that's what part of my research was, we stick a protein in a crystallized form here. It's in this shape. It's got hydrogen atoms all the way along it. We obviously can't see this with our eyes because it's tiny. Can't even see it with them. You can't see it with your eyes, even with a microscope. So I shoot X-rays through it. The X-rays bounce off the electrons, and based on the X-rays that don't hit this, we can determine the shape. So that's how we know that there is an electron cloud, because we can produce images of what something might look like based on where the X-rays did not pass through. Because of this cloud of electrons that is surrounding the atoms. So the cloud model, you've got the nucleus, 3 energy levels, one over here, one over here, one over here. So it creates a random cloud of electrons, and unless you go into some weird quantum physics, then we can't predict where the electrons will be at any given time. It'd be nice if we could. So in 1932, so where are we at now? We are just the proton, and then we've got electrons. So negatively charged electron. But it wasn't explaining the mass of an atom. So the protons and electrons simply weren't heavy enough. And so he put that there is neutrons. These are little particles, and they do not have a net charge. So they're not negatively charged. Usually, so hydrogen, there's 1 neutron, 1 electron, 1 proton. And then you can continue to count from there through the periodic table. So now we're at our modern understanding of what makes up the atom. I know anyone who studies chemistry with me will know just how much I love to go on. Ah, there's more people who have joined I haven't seen. Hi, Madison and Cooper. Sorry, I got in the zone then and didn't even see that you guys had joined because it doesn't show up because I'm recording. I did give 5 minutes, sorry. Right. You can watch the recording. We can You guys got your notes in front of you that I sent out today. That would be helpful. So now we know how we came to have our one understanding of the period, not the periodic table, but of the elements. Sorry. One understanding of the atoms. Now we look at the periodic table. So a guy called Dmitry Mendeleev. Mendeleev, yeah. He took all the elements and just listed them in increasing atomic weight, and what he assumed was the increasing atomic weight. And he left a lot of spaces on the periodic table. And aside from some of the weirder ones and stuff that we've created in the lab, he got most of them right. So he put them increasing atomic weight. So weight. We then put them into groups. You see all those groups. So I know there's 18 groups, but we don't worry about the transition metals for Europe, even up to first year uni. The only thing you'll really need to know in there is copper, iron, silver, chromium. I don't know chromium is not even transition metal. So he arranged them into groups. Now that we knew what the atoms were, what they entailed, we put them in increasing atomic weight going that way. So 1 here, 118. Down the bottom. So this works, but not really. So they thought, you know, so we need to put them into periods, hence the name, periodic table. So he put them in increasing atomic weight. We put them in increasing atomic number. And an easy way to cheat, remember what that is. Atomic number is the number of electrons, which would also equal the number of a number of other things. So I'll let you figure that out. So groups going down. The groups he did based on the reactivity or their valency. So group 1 has 1 valence electron. Group 2 has 2 valence electrons. Group 3 has 3 valence electrons. 4, that continues all the way across to 8. He knew that the noble gases didn't react. And this is important for next week. Well, actually not next week. I'm going to record it this week because I'm away. But this is the state that all the other atoms are trying to get to in group 8, or what we call the octet state. So we have periods now that run across this way, 7 of them. So we have 7 periods, and if we think the layers of the onion, each one of these adds an extra layer. So this has, so hydrogen is atomic number 1. Group 1, period 1. Group 1 is the alkali metals. Very, very reactive, very explosive. Hydrogen, sodium, lithium. Throw sodium into water and it will react with the water to create a fireball. Hydrogen, if you light a balloon of pure hydrogen, you'll get a massive explosion. Alkali earth metals. Oh, one thing these guys never, ever found in nature by themselves. They are so reactive that they will react with just about anything, including themselves, to try and stabilize. Group 2, alkali earth metals. Still metals, but they aren't as reactive. Still quite reactive. Magnesium and calcium, 2 metals that are required for life, are in this one. So group 3, if we go 1, 2, and we skip all the transition metals, we get to group 3. Not much to say about group 3. What's the group 3 metal? Anyone? Completely blank. But they're pretty unremarkable. I can't even remember one, so they're not very remarkable. Group 4, the carbons. Probably the most important. I mean, they're all pretty important. But for biology, carbons are very important. Silicon is used in superconductors. Well, not superconductors. It's like a semiconductor and it's used in computer parts. They have 4 valence electrons. So carbon can form 4 bonds with other things. And when we go through a little bit of organic chem later on, again, another probably double up week, we'll probably do 2 hours worth of this. 1 live and 1 pre-recorded. Group 5 has nitrogen in it, has boron in it. So nitrogen, again, another one that's quite important in biology. Group 6 is oxygen. So we start looking at the gases now. Oxygen has 6 valence electrons. Group number 7, the halogens. Fluorine. So now we're into the gases big time. Fluorine is the most reactive element. Aside from some very, very specific conditions, you cannot keep fluorine in fluorine state. It will react with just about anything to produce hydrofluoric acid and it will burn its way out of anything you try and keep it in. Again, it'll only, you won't find it by itself. It'll always be reactive with something. So down here on the left, remind me, on the left here, bottom left, there we go. Bottom left here, we have francium. And here we have fluorine. There is another trend on the periodic table called electronegativity. And it goes from here to here. And it's a really good indication of how reactive something is. Francium virtually doesn't react. Fluorine will react with anything it possibly can to try and destroy whatever it's in. I mean, it's not doing that intentionally, but just how it is. So these guys, group 1, will produce +1 cations when they react. these guys will fall into +2. These guys -1, -2. These guys -3 or +3, depending on what the bond is. Again, important to note for next week when we look at things that bond. So, and I'll relate that to where they sit on the periodic table as much as I can. Okay, I'm going to go on the last slide. There's a little periodic table. It's really cool. Periodic table like you've never seen it before. Thank you, Jacob, for putting me onto it. It's really cool. So you can see the properties of the different elements and what they look like and why they're all grouped together. So the alkali metals here, they're metals, but you can actually cut them with a butter knife. So they're soft, they're malleable, and we'll learn next week when we go into metallic bonding just why metals act the way they do. So hydrogen is number 1, helium is number 2. These guys do not react. They are the noble gas. They are in an octet state. This one really grinds my gears when people use helium for birthday parties. It's a very, very rare gas now. We have to mine it, and it's important in medical imaging. Neon, same thing. Argon, again, same thing, although we don't fill it with balloons. Xenon and krypton we use in, you probably don't see them now anyway, but the lights that flicker, the ones that are always flickering in scary movies, that's argon and neon, and they're usually flickering because they've run out of the gas. Xenon, radion is a radioactive gas. The fluorines, the halogens, there we go, got that in the end. All very reactive. So chlorine, fluorine, bromine, iodine is very important for biology as well. These three are very, very reactive. We can take sodium from group 1, which is very, very, very explosive, poisonous. Mix it with chlorine, which is used to gas people in the war and to clean our pools. And we can mix them together and make table salt. Something that makes food taste better. And next week, again, when we look at bonding, this will make a lot more sense. Oxygen, obviously. Oxygen and sulfur. There's bacteria. If you go to, there's certain foods that when they go off, they smell like rotten eggs, including eggs, because they go rotten. It's because there's bacteria in there that have evolved to, instead of using oxygen, they use sulfur. So they're right next to each other on the periodic table. So they're called anaerobic bacteria. So then we've got the nitrogen, the nitrogens, phosphorus. Phosphorus is red phosphorus is used for matches. So the red on matches is phosphorus. Carbon. There's a theory that on other planets where there's no silicon, where there's no carbon, that silicon would be carbon's replacement in life forms on those planets. Yet to prove it, but here's where things get weird. You've got carbon here, the giver of life, creates life, is the only reason life exists. And then you have lead in the same group, which is one of the most toxic things. There is no safe level of lead. And you can see there we used to use it in pipes. So thought that would be a good idea. There we go. Aluminium is what I wanted. Aluminium. Might make cans out of. So most of the periodic table is made up of metals. You've got the alkali metals, the alkali earth metals, the transition metals. And then along here it gets a bit weird. Silicon, germanium, and a couple of others that I can't remember now, are what are called metalloids. So they exhibit both the metals properties and the properties of non-metals. Germanium is what is used in your smoke alarms. Not so much anymore because it's radioactive. And we come over here again. The only transition metals that you really need to know for 11 and 12 is zinc, copper, maybe nickel. And it's where they'll try and trick you with the naming. So gold, symbol for AU, oh sorry, symbol for gold is AU, AG for silver, HG for mercury. And then we have the alkali metals. So calcium, magnesium, both vital for life in the right concentrations. Radium's an interesting one. Up until 50 years ago, they used to make the watch, the clock faces, and the hands on the watches used to glow green because they had radium. If you buy an old clock and you run a Geiger counter over it, it will go mad. And I'll finish on a bit of bonding. So things bond together to try and get to this state. So the elements bond together to try and get to the octet state. And this is a segue into the next one I'm going to put up, which will probably be about an hour and a half, or maybe 245-minute ones, otherwise my brain will show. So group 1, hydrogen and fluorine. So hydrogen has 1 electron in its outer shell. It needs 8. Sorry, it needs 2. Hydrogen's the only one that doesn't need 8, it needs 2. And there's boron, which needs 6. For the sake of your course, all of them need 8 except for hydrogen, which needs 2. Sorry, I had a moment there. So I take sodium, which has 1 electron in its outer shell. And then we take chlorine, which is directly across it in the same period. It has 7. So it either needs to gain 1 electron. So sodium comes up to chlorine. Hey, it's going. And he or she, sorry. Sodium gives the single valence electron to chlorine. Chlorine gains 1. It's now got 8. Sodium loses 1. It also now has 8. Sodium is never going to try and gain 7 valence electrons. It will always lose 1. So if we remember, always have a 1 plus charge, always have a 1 minus, come together, and they make sodium chloride. So a delicious tasting substance out of two very, very poisonous. And that's ionic bonding. So we'll go through the 3 types of bonding in the next one. It's when it gets really, really in depth, as I'm sure you've seen if you look at the slides. So magnesium oxide, always 2+. So magnesium is always going to be 2+, oxygen is always going to be 2-. Hey, look, MgO or magnesium oxide. So the reason that things react is based on where they sit in the periodic table. And I am going to